All right. So what we were just saying was that, oh, you know what? Maybe just a clarification. There was a question. Didn't we use Fs for static friction? That's true, but in context, we're talking about this as being a spring force. So in context, you need to know that this Fs is spring force. Now, there are some people that say, well, hey, if there's static friction as well, could we come up with something simple just to like make it so we don't have to have weird subscripts? Sure, you can use Fe for elastic force, E for elastic, but also recognize that if I have charged particles, it could be an electrostatic force, this Fe, right? So if you have a spring force, a static friction force, and an electric field force all going on at the same time, you might need to write some more complicated subscripts, that's all. We try to keep it to one letter just to make it easy on ourselves, right? So, yep, you're right, Fs could be for spring or for static friction. Okay, so I got a graph here, and it says try to explain in your own words what's being shown in this graph of a spring distortion. Now, before I let you guys just describe it in your own words, I'd like to ask, over what region does this spring behave in an ideal way? Look, like if I write this at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, when is this spring behaving in an ideal way, according to Hooke's ideal spring law, or spring law for ideal springs? I heard 1 to 2. Is there anywhere else where it's ideal? Yeah? 6. Yeah, you know what? Let's see. An easy way to check is to just put a ruler next to it. Can you guys see that from 1 to 2 it's straight? From here to here, see how it's straight? That's ideal. I'm going to put a dot there. Looks like from there to there, it's ideal. And so people say that a lot of springs have a range over which they'll behave in an ideal way, and beyond that range, they won't behave as an ideal spring anymore. Somehow the spring starts to break down, or you've kind of overextended the spring. So it's got an ideal range. Now, if I put my ruler up to it again, can you see that it's straight for that portion as well? So I could put like a little dot here, and I could say, okay, well, it's kind of ideal there, but notice that it doesn't go through the origin, but at least it's going to be linear. So I could say that it's linear in this range here. It is linear. The rest of it's non-linear. And so what I could do, if I was talking about just what's happening with this spring, look at the steepness here. Look at the steepness here. Look, I can even color code it just a little bit. I'll do a little bit of pink here. Maybe I'll make this top one be yellow. And maybe I'll come in the middle and just, let's just say in the middle, I could put in like a tangent to that curve, just a little kiss right there. You notice that I could have 3 different K values I could talk about. Now obviously in the curved part, it's a transitioning K value, right? But I chose the midpoint on purpose. So I could say, hey, there's Ka, there's Kb if you like, that kind of average point, and then there's Kc. What we said earlier about the stiffness.
Interruption.
Hello.
Hi, I'm looking for Madeline Ainsworth.
Oh, yes.
She come down with student services.
Sure,
please?
yeah.
Thank you.
All right. So what I could say here with the springs is as things proceed, the K value is changing. And so let's just put it out there. At position A, B, and C, where is it the stiffest? Hey, look, it's harder to stretch. It's got more slope, higher slope, harder to stretch. Yeah, we'll see you again soon, okay? We'll go to the other extreme. At C, isn't it going to be easier to stretch? Lower slope. And remember, the units for these K values are units of newtons per meter. So it's going to, if it's a steep slope, take lots of newtons per meter to stretch it. Less slope, less newtons per meter to stretch it. And then I could say in between, well, it looks like it's going from hard to stretch to less hard to stretch. Could I maybe say something a little bit more everyday, like this spring is giving out? It's getting easier, yeah, getting easier, or it's starting to give out in terms of its strength, okay? Getting easier. It's a transition. And then it happens with springs, just like any other thing. It's going to have a material breakdown, perhaps, and it lets go. I can think of like a situation for me, sort of an elastic material that starts off hard to stretch and then becomes really easy to stretch. Think about like a marshmallow. Can you imagine like a marshmallow is hard to stretch at first, but then it starts to like become stringy and fall apart on you a little bit and becomes like really easy by the end? I'm sure you can think of other things too. That's just the first thing that comes up. And marshmallows, delicious. So let's go back to this idea of a graph. This linear graph. Let's stay ideal again. If I were to have an ideal spring, we all are in agreement that the slope of this spring would be delta Fs. And, sorry, the rise would be Fs, and the run would be this weird delta of delta x, the change in the changed length. So that our slope ends up being what we're calling K, the elastic coefficient, Fs over delta x. And what we've said earlier is that K ends up figuring into the linear equation, Fs equals K times delta x. Really, we're just rearranging this slope ratio. And then everybody seems to be doing it. They put a negative sign out front to indicate that it's a resistive force. Even though I'm fully acknowledging the slope is definitely positive, right? We're just putting that in as a reminder for ourselves. So for any ideal spring, the slope is quote unquote K, and it's a constant specific to that spring. Okay, this is not a universal constant like universal law of gravity or something. Every spring is going to have its own different stretchiness coefficient, its own elastic constant. And that slope, delta Fs over delta of delta x, is going to have the units of newtons per meter, or newtons per meter, like, oops, capital N, whacked together. And it's a description of the number of newtons required to distort the spring by 1 meter. I know, I feel like I'm slow talking this one, but if you like, it is a stretchiness rate. Now, it's not a complicated formula, so I'm not doing a bunch of example problems. I'm going to leave the homework for that. I want to talk about something else a little bit. That was all slope stuff. That was all slope conversation. And what we've done in the past with different graphs has been to find the slope of the graph and discuss its meaning. Another thing we've done is found the area of a graph and discuss its meaning. So I want to take the exact same graph. And I've taken this linear graph we've got here, and I recognize that at the maximum stretch, see where this dotted line is? That's when you've maximally stretched this spring. You've gotten out to the end of its ideal stretch length, if you like. It would have a height of what we could call Fs max. You know, you've maximized your stretch. There's going to be a maximum force. That's the height of that triangle. And delta x max, even though I pointed at a dotted line, we could think of that delta x max, that maximum stretch, as being the length of the base as well. Now, if I'm trying to find the area of this triangle, area has been useful in the past in kinematics, but every time we find the area of a triangle, base times height divided by 2, or some people write it as 1/2 base times height.
Sorry, can I leave this?
Yeah, of course you can. Of course. So 1/2 base times height, if I replace out the base and height variables, then I can say, all right, well, that's 1/2. Remember, the base is delta x max, and the height is Fs max. I'm going to call that equation 1. But then I also want to pull out an equation 2. That equation 2, oops, sorry, equation 2, I'll put a 2 in a circle. Equation 2 would be Fs max equals K times delta X. That's just Hooke's ideal spring law. And I'd like to sub 2 into 1. And if I do that, I end up getting that the area is equal to 1/2 delta X max times, instead of just Fs max, I would write K times delta X max. And then, of course, I got to group together the like terms, so I get 1/2 K times delta X maximum stretch squared. Which is actually not that bad an equation. 1/2 K delta X squared. But I got to do a quick little aside about this one. Talk about what's the area mean. What does the area mean? So if we have this 1/2 K times delta X squared, it turns out that if I break this down by units, the units for K, we already talked about this, are newtons per meter. And the units for delta X squared would be meters squared, right? Because it's meters times meters, meters squared. And so that means that that would be, well, newtons per meter times meters squared ends up just being Newton meters. Because the meter in the denominator and the squared cancel each other out. I'm going to pop that up here and say, okay, well, I want to blow up the newtons and make them be kilogram meters per second squared. That's what a newton is, a kilogram meter per second squared. That's what's buried in the newton. Times meters, and we end up getting kilogram meters squared per second squared. Now this is something that you may or may not have encountered before. Probably not. But a kilogram meter squared per second squared is actually the long form version of another unit. Starts with a J. Does anybody happen to know what I might be? It is joules. Yeah, turns out it's joules. Joules, capital J. It's somebody's last name, just like Newton is a person's last name. Capital J for joules. And so buried in a joule is kilogram meter squared per second squared. So really, when we calculate the area under one of these force versus delta X triangles, we're calculating the amount of elastic potential energy that's being stored. And you can store energy in a rubber band, if you like. You could store energy in a spring. And nobody's surprised by that, because if you take a spring and you squish it down and then let it go, it's going to spring away. It must have energy stored inside of it. So what we're going to say is that we'll come up with a new equation then. Instead of just calling it area, we're going to call it spring energy, 1/2 K times delta X squared. I'll put a box around it, and anytime you distort a spring, you're storing elastic potential energy inside of it. Elastic potential energy. And I mean, this is specifically for an ideal spring.